So, hello everyone. I'm Jinjiang from Inner Mongolia University, China. Today, I'm going to introduce the DRC-NET hearing aid speech enhancement system that we proposed for this challenge. So, I'm going to start with the system overview and then introduce the TF domain low latency OLA strategy for neural network-based algorithms. After that, we introduced the DRC-NET that we used for the speech enhancement. Finally, some other details about model training and results. So this is the system overview of our hearing aids algorithm for this challenge. We first downsample the microphone signal to 22 kHz, and then using the STFT transform the signals to the time frequency domain. In the time frequency domain, we use a DRC-NET as a fixed neural network beamformer. As you can see, our system does not use a target speaker information or head rotating signal. DRC-NET will take the complex spectrum of BTE microphones as input feature to predict the clean complex spectrum. After that, we used NALR method to adjust the frequency response of the output audio to match the different hearing loss characteristics which have been provided by the challenge baseline system. We will not introduce here. In the domain transformation, we proposed a low delay STFT analysis and the synthesis strategy. So typically, system use STFT for speech enhancement in frequency domain have larger window size to ensure good frequency resolution. This will lead to long system delay, which cannot meet the real-time requirements of hearing aid system. In order to solve this problem, we proposed a low latency analysis and synthesis strategy for neural network-based algorithm. In this strategy, the system delay is only depend on the size of the frame shift of the STFT. So we use the 23 millisecond window with a frame shift of 5 millisecond frame shift. First, we will emit 18 millisecond zero signal at the system's start. And you can see when 5 millisecond signal is cached by the system, they're concatenated, and then we get the frame 0. This frame can then be processed using neural network. And then we get the output frame 0 in training stage due to the padding is not applied to the training target. So the first 5 milliseconds of the frame 0 is used to predict the target clean speech. When another 5 millisecond segment comes in, we get frame 1. Similarly, we use neural network to process it and get corresponding time domain output signal. And again, we use the beginning 5 milliseconds and the corresponding segment of previous frame 0 to overlap and add. And the OLE result is used to predict the clean speech of the second segment. Similarly, when we process the frame K, the first 5 milliseconds of current output frame and the corresponding segment of previous frames are added together as the output to estimate the clean speech in this 5 millisecond segment. So we basically use current 5 milliseconds segment to predict its clean signal, and use the historical 80 millisecond segment to increase the frequency resolution in the TF domain. And the rest 18 milliseconds of neural network output is used at the prediction of the future signal. to smooth the estimation result. By this way, the delay of the system can be determined only by the side of the frame shift, which allows us to use large window lengths to ensure good frequency resolution. And it's not only beneficial to speech spectrum modeling, but also crucial for spatial information-based speech enhancement. Another problem is the window selection in STFT. We commonly use a symmetric window like Henning, Hamming, etc. Here, there's a problem using the symmetric window function. As you can see, since the target segment is close to the window's edge, the symmetric window function suppresses its energy, which results in a loss of crucial information in the target segment. Moreover, in inverse STFT, the process of signal synthesis by using overlap and add symmetric window function results in more weight being given to the predicted signals instead of the mapping signals. However, and this could cause the severe performance degradation. Although we could design a handcrafted asymmetric window like this, it's difficult to adjust the window curve to reach best performance. Here, we choose the rectangular window. We believe that neural network can handle the energy leakage and adaptively adjust its output for good synthesis result. Now let's introduce the DRC-NET. The DRC-NET is an end-to-end frequency domain model that we used for speech de-reverberation in ICASP 2022. So it's a model with common UNet structure, and the dense blocks are inserted into the UNet structure, which we call the DRC block. The major differences here from its original version is that we did not downsampling the frequency dimension at the model's input layer, which will have better spatial directivity. And later I'm going to explain why. And in this model, we use GRU instead of LSTM. As you can see, the basic processing unit in DRC block is the RC unit. So let's take a closer look at the RC unit. As you can see, in RC unit, we have a channel-wise GRU and then followed by a convolutional layer. The channel-wise GRU means that the GRU only processes one frequency being at a time and take the channel dimension of the frequency being as GRU input feature. As you can see, there are two types of RC unit. One is the RCF unit. This means the GRU processing the frequency dimension. In RCT unit, the GRU processing along the time dimension. This respectively processing each frequency being approach actually come from our previous work called the in-place CRN model. As we know, in a common CRN model, the downsampling operation in frequency dimension is crucial for better full band spectral modeling. But as we know that the former process each frequency being and form beam patterns for different frequency respectively. This is because spatial information is represented by the phase difference at each frequency being between the multi-channel spectra. So spatial information therefore independently exists at each frequency being, but the downsampling operation in frequency dimension could lead to spatial information loss. So we designed the in-place CRN model first to preserve the spatial information. We discard the downsampling operation in convolutional layer. As you can see, we call this convolution the in-place convolution. And then to process like informer, we use channel-wise LSTM to process spatial information in each frequency beam. This work shows that downsampling could lead to severe spatial information loss, and this in-place approach has very good spatial directivity. We also find it works great for acoustic echo cancellation. This in-place processing style is not just used for neural network beamforming. It also works for dereverberation. For example, traditional dereverberation algorithms like WPE independently process proposed linear prediction on each frequency beam, as you can see. This is because the convolutional reverberation can be modeled in TF domain as independent process between different frequency beams. Moreover, the reverberation process in different frequencies could also be different due to the different reflection materials. Another important fact that DRC-NET combines RN and CN together. RN can accumulate infinite history response for long sequence modeling, which is more effective than CNN and not require cache history features. However, RN is based on memory. Local details thus cannot be fully preserved, and CNN has better ability to model local details. Moreover, dense connection enables such a deep RN network as smooth gradient transmission. In addition, as there is no downsampling operation in the dense block, as we have introduced, it has good spatial directivity and can process reverberation more effectively. In our training, MAE is used to constrain the real part, imaginary part, and the compressed amplitude spectrum of the signal respectively. This constraint of real and imaginary part is beneficial to ensure good phase estimation and a better spatial hearing experience. The constraint of compressed amplitude is helpful to improve the auditory quality of the NAR output, because most NAR prescriptions amplify energy at medium to high frequency band. So this is our model complexity. The total parameter is 1.9 million, and the Haspa score of development test set is 0.71. So our conclusion is why DRC-NET works is because it has in place characteristics independently processing each frequency beam. Thus, it have a good spatial directivity and can effectively dereverberation in each frequency beam. And besides, we combine RN and CN together to get a much powerful neural network. Thank you. This is my sharing representation.
So if there are any questions, feel free to raise your hands or post something in the Q&A. There's nothing popping up just now, so those are the standard questions. Was there anything in particular that you found challenging with the challenge?
Well, I think the major challenge is that it's difficult to achieve low latency in the time frequency domain approach. And the small window function does not allow the frequency domain algorithm to achieve full performance release. Of course, we finally used the low latency strategy we introduced to solve this problem.
And I noticed when you were showing the window function that you used, you had a that one there. So you've got a kind of like an exponential function traced over there. Was there any reason you didn't sort of use that function as a window rather than using the rectangular window?
Because if we use this kind of window, we need to handcraft and adjust this its shape. It's quite difficult to determine whether how to design this shape to get the best performance.
Okay.
Mm.
I see Samuel Cornell.
Yes, yeah, thanks for the great talk. I didn't understand quietly how you do the low latency overlap path. Like, do you predict 18 frames in the future, or?
Yes, it's
Okay.
actually overlap to the future
Okay.
segment, but we didn't think that this neural net could predict such long segment. It could predict the stable signal components just to smooth the estimation.
Yeah, makes sense. Thanks.
Well, thank you very much. Thank you very much for the talk and the presentation.
Yeah, thank you.